Awesome. Thank you guys so much for coming. So what this talk is really about is kind of talking about how do you start using graph data instead of tabular data in a machine learning pipeline using Spark and Neo4j to make better or different kinds of predictions than before. And so whenever I give this talk, what I really like to start out with is the one slide where if you start looking at your phone as soon as I finish this, you still get the take-home message. So this is the TLDR slide. When do you need to use a graph? And I really like this aphorism. This is kind of like an American saying, it's not what you know, it's who you know. When this saying is relevant, a graph is probably going to help out. So an example I like to kind of give is if you think about how did you get your last job, right? You can talk about, well, where did I go to school, or what did I get a degree in, or how many years of experience did I have, or what was the awesome company I just worked at, right? Those are all probably pretty relevant. But I bet a lot of people in this room have gotten a job because they had a friend at the company who referred them, or their former boss was a mentor who said, I can help you with this. I can help refer you for this interview, or someone you went to university with, your old roommate worked at that company, right? So it's not just the tabular data of, how old am I? Where did I go to school? What did I study? It's also those connections. So when connections matter, graphs are probably helpful. And another kind of less hand-wavy example, so we can kind of bring it back to reality, I like to talk about how do you predict if someone is a smoker or not. And so there was a big study by the NIH in the US where they tried to figure out, how do I predict? I don't know anything, I've just got some demographic data. How do I predict if someone is a smoker? And I bet every data scientist in the room is like, easy, right? I've got their demographics, what's their race, what's their gender, how old are they, where do they live, how much money do they make? I'm going to throw that all in, I'm going to do some variable selection, it's going to be great. They actually found the single most important predictor was whether or not your friend smoked. So it's who you know that determines your outcome. So this is like the take-home message. Graphs are important when connections matter. And so you're probably like, cool, does this matter for me? And I like to kind of start with an overview slide of just 8 different verticals where I have seen or used graphs to improve predictions for data science. And this is not saying outside of these 8, there's nothing here. This is just a really nice broad segment to kind of cover the full spectrum. So if you've ever heard folks from Neo4j talk before, we talk a lot about financial services and fraud detection, right? So how do I predict if this transaction is fraudulent? Or I have a whole bunch of transactional data, who's transacting with who? How do I know where money laundering is happening or where someone is creating first or third party fraud? So financial services is really one of the areas we started out in, and you can think about finance is really nice for a graph. You have people, you have them making transactions, they have identifiers, you have all of these interactions. And you can pull out graph-based features like topology that are really predictive. And we're going to talk about this more a little later. The second area I like to highlight, because this is where I come from, is drug discovery. So my background is actually biology and chemistry. And if you think about that, all of that is a graph, right? You have systems biology, you have genes that interact with proteins that cause outcomes, you have chemicals which are themselves graphs. And a lot of stuff in the R&D sector and drug discovery, a lot of new advances are being driven by knowledge graphs and mining knowledge graphs and doing link prediction to find new and novel interactions. Recommendations are another totally different area from drug discovery, where historically speaking, we would talk about something like collaborative filtering. So that's, customers who bought this item also bought that item. And I'm sure you've all seen that on Amazon. But you can make that better with graph data science. So instead of just saying, okay, let me filter this data, I could instead say, well, how do I predict what's actually most influential for you? So maybe I want to say, who is the most influential customer in my graph? And maybe their purchases are more significant for you than someone else's. Maybe the purchases of your friend matter more than me. Who knows? And I'll talk about an example of this with graph embeddings later on in the talk. Customer segmentation is a little similar to recommendations, right? It's how do I break down my customer base into relevant groups? And this kind of goes back to that smoking example we started out with. So I have a bunch of people, how do I break them out? Traditionally, you'd say, okay, I'm going to say geographically, demographically, based on tabular data. Another thing we're seeing a lot of especially in churn prediction, is I want to actually segment my customers by who they know and who they interact with. So instead of saying I want to talk to all of the white females who live in Brooklyn, I could say, well, I can look at who's calling who in my graph, and I can segment into these people interact with each other. So I can target messages to people who are friends, not just people who look the same. So cybersecurity historically has been a big area for graph-based data science. This is if you think about, traditional network intrusion, right? Is this network safe or has it been corrupted or compromised? And so you have a graph, and in this case you have, this is what my normal graph looks like, and I can train a model to say, has this graph been compromised? I can say, what are the outliers in this topology, or what changes signify something has gone wrong? Churn prediction, I already talked about this a little bit. We're seeing a lot of interest in how do I predict which customer is going to leave my network next. So I've worked on this in banking as well as in telcos, and this is really, I have this data about who individuals interact with, what services are they interacting with, have they called my customer support center, what has been their customer journey through my network. And you find that actually a lot of these graph-based features are super predictive. There's actually a really good paper from Huawei from a couple of years ago where they looked at what's the most predictive feature of who's going to leave next. And it was if someone, the most influential person that you called, if they left the network, then that is a really significant predictor of you leaving the network in the next month. Search and MDM is an area where a lot of this got started from. So you will probably hear me say PageRank like 20 times in this presentation because it's a graph algorithm everyone knows. PageRank is how Google got started, right? That's how you search through your data to find the relevant piece. Master data management is similar. This is just using a graph and exploiting the topology to make better predictions about what's relevant for the question you're trying to ask. And then finally, in a really different vein, you kind of have predictive maintenance. So this is, I have a system and I want to know what's the bottleneck or what's the weakest point so I can intervene before I have a network failure. If anyone here kind of works in operations research, supply chain management, you might be much more familiar with this piece where I have interacting dependencies and I need to figure out which one do I need to be proactive in interacting with, where's the bottleneck, really what's the flow of interactions across my network. So this is just 8 things. You can ask me later. I can probably come up with a use for graph for most things. When relationships and connections matter, graphs are probably helpful. And I just added this slide in because I realize not everyone works at Neo4j and spends all of their time staring at graphs. So when I say graphs, what do I mean? What I'm talking about is a labeled property graph. So you have nodes, which are like your individuals. So I've talked about person interacts with another person. So your person is your node, and they can have labels to classify them. And then you have relationships, which are the types of interactions. And then on your nodes and your relationships, you can have attributes and properties. So, we have a person node, their name is Dan, they have a birthday, they have a Twitter handle. They have a relationship with Anne, that relationship is married to. And you could actually say, they were married on this date and add another property. So this is just a really nice and intuitive way of connecting your data, right? So this is how do I represent connected data in a way that's optimized for these traversals and graph-based queries instead of going back to rows and columns in SQL land. And the reason Neo4j is here is we've actually been working on building Cypher for Apache Spark. So you can now lay a property graph kind of projection on top of a data frame. And I'm going to talk more about that later. But how do you take your data, transform it into a graph, and start interacting with it? And so what am I talking about with data science? So we know what a graph is. Hopefully I've convinced you that maybe they're useful for some things. But what am I talking about in practice? So what I am not saying is to throw out everything you've done. I bet a lot of you, if you work in data science, have existing model building pipelines. You have models that work and they're predictive. We're not saying there's no value there. What I'm saying is that graphs can actually help you make better predictions with the data you already have. So I work on the graph algorithms team. What my team does is we have a library of algorithms that can extract information about the topology of your graph. So something like PageRank or centrality estimates. You can put that into your tabular data, add more information, new predictors, new features to make better predictions. So we're not saying throw out what you have, just make it better with graphs. The other thing you can do that I think is really cool is when you have graph-based data, you can start making graph-based predictions. So my background is actually knowledge graph completion, so link prediction, right? I have a graph of who knows who. I want to predict who's going to make a new friend in my graph. So who is going to interact in the future? I want to predict new relationships. When your data is in a graph, you have relationships. They're first-class citizens. You can start making those predictions. So the bottom line is you can use graphs to add new features to your existing models. You can also start predicting new types of things about interactions and relationships. And in case you're like, well, Neo4j just really wants to convince everyone graphs are a thing, they're totally making it up, why am I sitting here? It's not just us. There was actually a really awesome paper that came out November 2018 about relational inductive biases, basically proposing that graph networks are a really good generalizable approach to machine learning. So instead of spending all of your time in row and column land, when you have graphs, you can generalize and have much more flexibility in representing your relationships. And this is a quote from the paper in the black box. Graphs bring an ability to generalize about structure that traditional neural nets and kind of row and column just doesn't have. But what was super interesting in this paper, it was a position paper, it said, here's a framework for how you do this type of modeling, was the thing on the other side in the red. So the bottom line, they said, was not how do you model with graphs, it's where do you get the graphs to actually run these models on, right? So we all spend our time, or I spend a lot of my life in SQL and data frames, right? So my data is in a table. Where do I get a graph to even do this with? The reason this paper was super exciting to me is I work at a graph database company, right? We have the database to store your graph. And you can kind of combine the power of machine learning with the ability to represent your data as a graph to make better predictions. And if you're wondering, okay, how does this actually work? I've seen a lot of cool clip art, I've seen some quotes. What am I doing? What I'm actually talking about is how do you build a machine learning model? You start with your different data sources. So I have data in Spark, maybe it's already in Neo, maybe it's in some flat files. I'm going to unify that data in Neo4j. I'm going to use the graph algorithms library to engineer new features. And then I'm going to put that into my machine learning pipeline. So I'm already working in MLlib or I'm using scikit-learn. You're adding those features into that pipeline. Talking specifically about Spark and Neo4j, let's say you're starting in Apache Spark. Cypher 9 and Spark 3.0 will let you be able to take your data frame and transform that into a property graph where you can start doing, okay, what is the graph structure of my data? What are graph-based queries and what do they look like? And I want to start exploring simple algorithms and seeing what results do they give me back. Once you've done that, so I have my 10 terabytes of data, I've reshaped it into a graph of maybe 2 terabytes of what's relevant to me. I've subset it to what I actually want to run my algorithms on. You can then push that into Neo4j with Morpheus and start running native graph algorithms, persisting that database, and storing those predictions. And then once you've done that piece of work, you can take that data back out and put it into your machine learning pipeline. So this is just part of a workflow of how do I get started with graphs and what are the pieces that I'm putting together. And we're going to kind of revisit this for specific examples to just drive it home. So how do Spark and Neo4j interact? What we really like to say is when you're using Cypher for Apache Spark, you're exploring graphs. Spark is massively scalable, super powerful for data pipelining, has really robust machine learning libraries, and you can take your immutable data frames and you can project those into graphs. You can say, what is my graph architecture? Do I have a graph problem? What are some simple queries that I want to get running with? Once you've figured out, hey, this is the graph I want to run over, this is the question I have, then you move into Neo4j where you start building graph solutions. So once you're in Neo4j, we're a database. These are persistent dynamic graphs. You can save, update, modify. You have graph native query and algorithm performance. So we have graph specific data structures to optimize these multi-hop queries, these global traversals. And we have a constantly growing list of graph algorithms and embeddings to let you start doing this complicated feature engineering. So how do I get started? I've just hopefully sold you. Where do I even begin? I've said, okay, you should reshape your data into a graph and then magic happens. The way I really like to frame this is the steps of graph data science. So the first step is having a graph. Can't do anything until we have a graph. Building on that, you can start using queries to engineer your features. So I have my person knows person graph. I'm going to start using graph-based queries to say, who do I know 3 hops out who has this property? Building on that, you can start using graph algorithms. So instead of me saying, I know this, I'm going to write this query and run it, what I can do is I can say, cool, I have an algorithm that tells me about centrality or communities in my graph. It's an unsupervised approach. I'm going to run it, and I'm going to take that result and put it into my external workflow. Building from there, you have graph embeddings. So what a graph embedding is, and I'd split this out from graph algorithm feature engineering, is graph algorithms, generally speaking, are heuristics. They're algorithms where I say centrality is measured by this algorithm. I have defined it up front. I'm saying, in the case of PageRank, it's how many connections do my connections have and what are the weights, and I propagate that across the graph. Graph embeddings are learned on a specific graph for a specific task. So they're similar to the graph algorithm feature engineering in that they are a way of capturing the topology and connectivity of your graph, but they're a little more advanced technically as well as custom engineered to a specific graph. And then at the far right, you have graph native learning, and this is graph neural networks. This is what the Google paper was about. This is, I have a graph as an input. I want to make predictions about the structural changes of that graph, and then my output is a graph. But the point is here, each step in this cycle adds value. You don't have to say, well, I'm not at step 5, I should walk away. The rest of this talk is going to be walking through an example of each of these steps, how it added value, and how to get started. So this is a really nice framework for no matter where you are, there is a way that graphs can add value and a good way to get started. So the first step is querying a knowledge graph. So in order to do data science on a graph, you need a graph. We're not going to spend a ton of time on this, but I have one example I like to cite, which is basically the lessons learned knowledge graph for NASA. So if you guys have seen this before, bear with me, but NASA is, the US Space Agency. They had 50 plus years of data, right? So they had white papers, they had memos, they had documents that were scanned, they had, all kinds of things just stored as a bunch of documents. And the way that scientists tried to access that information is they could go in and they could type a term and they could search it and they would get back, oh, I typed in, capsule, I got 8,000 results and I have no way of figuring out what's important. So in 2012, NASA worked with Neo4j to take this giant document store and turn it into a knowledge graph. So what they did is they did topic modeling, they did some NER to identify key concepts, they did some TF-IDF to figure out which concepts are important versus what's noise, and they looked at what's referenced in each document. And with this, they created the lessons learned knowledge graph. And they actually said, cool, I made a knowledge graph. What's the actual value of that? Well, they were looking at how do they build upwriters for a capsule. And so in the US, we have not landed on the moon in a very long time. Thinking maybe we should try it again, I don't know. We don't know how to build the upwriters, right? So the problem was they know they need the upwriters. That's what keeps the capsule upright when it lands. You don't want it upside down. That would end poorly. No one knew where the documents were. Using the lessons learned knowledge graph, they actually found the data right away. They said it saved them over 2 years of work and $1 million. So this isn't fancy deep learning. It's not model building. It's I have a graph. I know the question I want to ask, and I know I should have the answer in there somewhere. Having the knowledge graph, having those relationship-based queries, lets you start by just getting the answer back out. So now that you have a graph, we want to start getting fancy. This is when you say, instead of I know the question I want to ask, I think the answer is there, I say I want to build a model. I have something I want to predict, and I have some domain expertise about it. So instead of just asking a question of the graph, I can write a query that adds a feature to my pipeline. And so the example we like to cite here is churn prediction. So I talked about this a little bit before. This is basically this example in a telecom network. Who's going to leave my network in the next month is a simple way of framing that. And telcos are really great because this is a natural graph. So this is an example of the actual graph that was used for one of our customers. It's pretty complicated. You have, companies are calling each other, there are connections, you have calls incoming and outgoing from different numbers. You can kind of simplify that to something a little more tractable of I just have phone numbers that are calling each other, and I have different ways of contacting. I could have a text message or a phone call, you have incoming and outgoing. And you want to use this graph to say, simple questions like how many calls or texts has an account made? How many calls or texts has a second degree neighbor or 2 hops across the graph made? How many of my contacts have left this in the last month? How do I step further out? And so this is actually a really natural use of graph. There was a really good paper from 2015 where they basically had a full telco data set. They had who was churning every month, and they were looking at what are the features we can engineer in the graph. So this is not graph algorithms. This is I'm a domain expert. I know something about churn prediction. I can write queries to pull out things I think are important. So they said things like, what's the delta of incoming calls for an individual node versus the total over a year? Or what's my degree? How many calls do I get coming in? How many calls do I get going out? So this is an expert saying these are features I think are important. They put them into their predictive model, and you can see that the 2nd through 5th most predictive variables are all graph-based, hand-engineered queries. So this isn't even I'm running an algorithm, I'm running some kind of deep learning pipeline. This is as simple as I know something about the problem, I know which relationships I think matter, and I'm going to put them in and see if they're predictive. So how do I do this, right? How do you get started with Spark? The idea is that in Spark, you're going to start merging your distributed data together into a data frame, reshape that data frame into a graph, start exploring Cypher queries. So with Cypher and Apache Spark, you will be able to run those match person who knows person where that person churned in the last month and start seeing what does that tell me, what can I get out. Once you've figured out the right graph that you want to run over for your problem, you move that data to Neo4j where you can start building more complicated optimized multi-hop queries, and you can persist your graph. So you have a mutable database where you have all that data. You can then export those new query-based features into your machine learning pipeline, add that to the data you're already using, and start making predictions. So next step in graph data science, graph algorithm feature engineering. So the difference here is before I had to be a domain expert, right? I know about churn prediction. I think this is a predictor. I've built this by hand with a Cypher query. Feature engineering is instead saying, I have this category of graph algorithms. They tell me, generally speaking, about the importance of nodes in my graph. I'm going to run these algorithms. They're unsupervised. They're going to give me some kind of metric. I'm going to put that into my pipeline. So we're moving away from hand-engineered to general categories of information that describe topology and connectivity. And I think I like this slide because I think it's a little hard to wrap your head around what we're saying. What we're saying is you're taking the data you have and you're making new and more meaningful features like clustering or connectivity metrics. And in 2 slides, I'm going to have all of the different graph algorithm categories. And we're just adding those to your tabular data. So this is the Game of Thrones social graph, who interacts with who. It's nice because it fits on a slide. All we're saying is, let's say I want to predict who's going to win the Game of Thrones. And that show is done, but there are no spoilers here. I start off with, how old is someone? What house are they from? What's their gender? Are they alive or not? And if they're dead, they probably can't win. So then I want to add more descriptive features about the topology of these interactions. So I can add something like PageRank that says who is most influential based on who they're interacting with. I can add something like degree centrality, which is just how many interactions has a person had. Or I can say communities, and this is basically, instead of doing something like clustering on your tabular data, so like I've done k-means, this is clustering based on relationships. So which sets of nodes are more densely connected to each other than the rest of the graph. And all we're doing is adding new columns. And so this is the categories of graph algorithms. I promised it was coming up. So this is a nice overview for what are the kinds of things you can predict out of the box from the libraries that Neo4j offers. We have community detection. So this is, again, clustering your graph based on relationships instead of attributes. So which nodes interact with each other. There are different ways of figuring out clusters, and that's why there's multiple community detection methods, either based on interactions, weighted interactions, how you calculate it. But basically, how do I subset my graph into these people are all friends with each other and these people are friends with each other, etc. You have centrality and importance, and I said I would say PageRank like 20 times, so I'm going to just say it again, add up that count. This is how important is a distinct node in the network. So I have every node, I want to know how central or influential is it. And these are algorithms like PageRank, betweenness, degree centrality. Adding an attribute that says, well, this node is really important for this reason based on this algorithm. You have pathfinding and search, which is I have some nodes in my graph. What's the shortest path between this node and this other node? Or looking at this starting node, what's the shortest path to any other node in the graph? Or can I access from this node to this other node? Optimal paths or route availability. You have heuristic link prediction, and I separate this out. So sometimes people hear link prediction and they think, okay, there's like we're training a classifier model. These heuristic link prediction algorithms are based on assumptions. So you could think of like triadic closure. So if you log into Facebook and it says maybe you should be friends with these people, right? And it's based on you have a lot of friends in common. So there's an assumption that if there are two nodes and all of their neighbors are overlapping, maybe they should have a link between them. So these are heuristic-based predictions of whether or not there should be links. You have similarity, which is basically saying, given a node in this graph, how similar is it to another node based on its connections? What are its neighbors? What are the relationships that it has? And then we have embeddings, and they're kind of that transition point between a graph algorithm and a deep learning approach. So this is a learned representation of the connectivity or topology of your graph, specific for a use case and specific for your graph. So how do I use these? I said I would get back to financial crime. I spend a lot of time thinking about fraud detection. This is a really great example because most banks already have fraud detection in place, right? You don't just have people stealing your credit card all the time. They have pipelines that either have heuristics, so if I see a transaction more than 500 miles away from this person lives above this cash threshold, flag it as fraud. Or they have an existing model that says if I see this pattern of behavior, maybe this is fraudulent. You have graph-based features that can improve the accuracy of these heuristics and these models. So depending on the thing you're trying to predict, there's different algorithms that are more relevant. But if you think about it as I have this network of accounts that interact with each other, they have identifiers, they transact at businesses and banks. It's all connected. So if I'm looking at something like first-party fraud, so I'm making fake identities on a real account as authorized users, you can use something like connected components to find disjointed subgraphs in your data. If you're looking at perhaps fraudulent activities, so transaction volumes are higher than I would expect, looking for outliers in people's behavior, you can use something like PageRank to measure the influence based on transaction volumes and frequency of transactions, not just within one degree, which is easy to do in tabular data, but stepping out across that whole graph topology. Louvain comes up a lot when someone is looking at money laundering, where you're trying to obscure the source of where did this money come from? What are these transaction patterns? I don't want anyone to know that the mob is buying, is paying me off, so I'm going to have their payment go to a laundry service, and then that laundry service makes a payment at a restaurant, and the restaurant makes a payment at a shipping company, and then that shipping company buys something from me. So that's a 4-hop interaction, right? And so what Louvain is it's a community detection algorithm that finds those dense connections between nodes where you have a fraud ring. Finally, you can look at something like Jacquard. That's a similarity algorithm. And you can say, okay, this account, I know it's fraudulent. They've already been flagged. They've been arrested. I know it's fraudulent. I know who they're transacting with. I can then look at my graph and say, what node, what other account in the graph has the most similar transaction history to this known fraudulent graph? So who is most similar and has not been identified as committing fraud? So depending on what you're trying to do, different algorithms answer different sets of questions. And this is not just Neo4j making stuff up again. If you search just graph fraud or anomaly detection, there are over 140,000 peer-reviewed publications, almost 50,000 patents in the last 10 years. There is a growing consensus that graphs are really informative. How do I do this? We're excited now. So it's the same process of merging your data in Spark, reshaping your tables into graphs, figuring out what your graph problem is. You can explore simple cipher queries and a subset of graph algorithms already in Spark. Once you figure out your problem, you move into Neo4j, your native graph platform, where you can persist your graph, run a larger set of graph algorithms, natively optimized to run over large graphs, write to your graph or stream your results, and then take your predictors into wherever your model building pipeline lives. So graph algorithms, there are a lot of them. I'm not going to read through these. This is just an idea of what algorithms does Neo4j offer. I think currently there are 45 different algorithms. We have 2 teams working on this, both our product engineering team, so these are the officially supported algorithms, they scale to terabytes of data, as well as our labs team, and this is our experimental kind of R&D team, and they are always putting out new algorithms. Hey, this is cool, we saw a paper about this, someone said they wanted to try this out. They're kind of our first pass incubator, and so we offer both. And then if you're interested in getting started in Spark, there's a subset of these that are available in Spark as it is, some pathfinding and search, PageRank, some community detection algorithms. So you can start exploring in Spark, move into Neo4j when you have more questions or you need more algorithms. So what's next? The first 3 steps were really kind of what my company has worked on, what my team works on, what we own. We're now transitioning into forward-looking. So what's the state of the science? Where are people moving? What's coming? And so graph embeddings are really popular. I spent a lot of time talking about them. Everyone wants them. Embeddings are just a way of transforming your graphs into a vector or set of vectors that can describe some aspect of the topology or connectivity or attributes of something in your graph in a machine-readable way. And so what this is you can have a vertex or a node embedding. So if anyone here has ever heard of deep walk, that's what this is a picture of. This is, I want to create a vector of numbers that represent the connectivity of every node in my graph. You can have path embeddings, which is actually where I've spent some time working recently, which is I want to describe a traversal across my graph. So I have, for example, a customer journey graph or a patient journey graph, and I have all of the interactions they've had across that network. And I want to then take that traversal, and instead of having, this really sparse matrix to represent it, I want to just have a fixed length vector and then maybe look at similarity between 2 patients. Or I want to say, take that as another feature in my machine learning pipeline. And then finally, you have graph embeddings, which kind of encode an entire graph into a single vector. So this is, I kind of come from the chemistry space. You can encode every molecule as a graph. Depends on your use case, which one is most relevant for you. An example I really like to give of how do you actually use these is from eBay. This was a publication that came out last year. And this is how do you do recommendation with a knowledge graph. So instead of just collaborative filtering saying, I actually know a lot about these things that people are interacting with. I don't just know that Alice listened to The Shape of You. I happen to know that it was sung by Ed Sheeran, who sings some other songs. He's a pop singer. He has this album, he has this label. That label also produces this song. How can I take all of those relationships and connections in that knowledge graph to make better predictions? And what they actually did is they did path-based embeddings, so traverse across this knowledge graph to figure out what's the context around the songs that Alice listens to, and how do I recommend another one? And I'm not going to walk through all the math here, but what they did is they basically looked at Alice and the song she interacted with, and they looked at all of the 1 to 6 hop traversals across that graph between the target user and the things that they knew she liked in order to find what do paths across this graph look like for things that she would interact with. And then once you've created that embedding, that path-based embedding that represents things Alice likes, you can say, well, what paths across this graph look like things she likes but hasn't listened to yet? So it's a way of extending instead of just saying, okay, people who listen to Ed Sheeran also listen to Taylor Swift. You can say, what are the characteristics of the songs that this person interacts with in the context of the whole graph? So how do I do this? So right now, same first steps as before, right? You start off in Spark, merge and unify your data, move to Neo4j to build your expert queries. And then what we're working on right now is starting to implement some embeddings. So we have 2 labs projects for DeepWalk and DeepGL. These are proof of concept prototypes. The engineering team right now is working on scalable embeddings that can actually be put to use. And then again, bring those into your machine learning pipeline. So the last step of graph data science, we've made it this far. What on earth are we doing now with graph neural networks? And this is graph is input, predictions on the graph is output. And this is a deep learning application. You're training a multi-layer neural network using gradient descent. You have hidden layers. And so in this case, you're thinking about, I have edges, I have nodes, and I have a global update. So graph native learning is when your deep learning model takes the graph as an input instead of taking some tabular data or a vector or tensor. You have a graph. You're performing computations on that graph, updating your graph, and then returning a graph as a prediction. So what on earth does this mean in practice? This is maybe my favorite example of the whole talk, but it's super technical. I'm happy to talk about it afterwards. Molecule predictions. So molecules are natively graphs, so I have different atoms that are connected to each other. Super easy to represent that as a small graph. I want to know, given 2 molecules or 2 reactants and a reagent, I mix them together, what are they going to make? So this is, each one of these is a graph, they interact and they make a new graph. So it fits into that paradigm of graph in, graph out. And what's really cool here is you can predict both given 2 input molecules, what are they going to make? But also, because this is graph native learning, you're updating your edges and your nodes as you make your prediction. You're able to predict how it's made, so the mechanism of synthesis. And in this paper, what they actually did is they asked medicinal chemists, blinded, they had hand engineered from domain experts. This is the mechanism that this is synthesized under. And they had predicted reaction pathways. And actually, the blinded tests, they couldn't tell the difference. They had really high accuracy with this graph native approach. What it looks like is you have your inputs, you start with your nodes, you have a probability of interacting with each one, you update your edges, and then you figure out, am I continuing or am I stopping? So this is a really cool real world use case of graph as input, graph as output. So stepping back, we walked through all of these steps. Every step has value. We're not saying this is useless until you spend 3 years of R&D and you're at step 5. Every single step, graphs add value, and there's an entry point where you can get started. And hopefully this talk has given you some ideas of how can I use Spark, how can I use Neo4j, and start thinking about relationships. This is my last slide. If you need more information, we have both business white paper references as well as developer resources like a sandbox to start playing around, community forums. We also have a book which is free for download, which is Graph Algorithms in Spark and Neo4j. It's really awesome. You should check it out. And with that, I am done, and I'm happy to take questions.
Hey, folks, we only have... Thanks, Alicia. We have time just for one question. I would suggest if you are interested, maybe catch Alicia during the summit. It's about lunchtime right now, but if there's anyone with a question, please don't forget to fill out the survey. But all right, I'm sorry.
I have a question. If I look at your workflow from Spark into doing machine learning analytics, do you really need Neo4j in between?
So if you're doing something complicated, if you're doing complicated multi-hop traversals or some of those algorithms that are not available in Spark, then you need Neo4j, as well if you need to persist your data. So I have this data frame, I've done these transformations, I now want to save it and interact with that repeatedly. That's when you move to Neo4j. And actually, there are 2 presentations tomorrow from my engineers who will be walking through the Morpheus project and kind of how you make those decisions of where you're moving and how to actually interact with Spark and Neo4j. So you should check those out.
Okay, thank you.
Great. Thanks, everyone. Enjoy lunch. Thanks, Alicia.